I'm Audrey. I'm a third-year PhD student at UC Berkeley in the RISE, or now known as the Skylab. I'm broadly interested in databases. I've been focusing on transaction processing for databases, and today I will be presenting TAOBench, which is a new benchmark based on Meta's social network workloads. So the agenda of the talk will first, I'll describe Meta's social network workload, why it's interesting. We'll go through some of the notable features we've seen. And then I'll talk about the benchmark and what we're actually open sourcing, including a scalable distributed framework for running requests as well as workload configurations. And finally, I'll touch on both the internal and external impact the benchmark has already had and its performance on different systems outside of Meta. All right, so social networks are popular, continue to be popular, and they're supported under the hood by large-scale geo-distributed data stores. And there's some examples listed here, but with the extreme skew and read dominance of these workloads, they can be especially challenging to support, and we'll touch on some of the reasons why. While there's a lot of social networks, there aren't actually that many benchmarks out there. So one of the most prominent ones is LinkBench, which also came out of Meta a couple years ago in 2014. And this was actually derived from just the trace of a single MySQL instance. So it's focused on the persistent storage layer, and as such excluded all requests that go to cache, which actually represent the majority of the workload. It also didn't have any graph level transactions, and it didn't have any information about sharding as well because it was focused on one shard. And we'll show that sharding is not just an implementation detail, but it can reflect user intent, privacy constraints, and such. So it's important to have this information for different purposes. Another prominent benchmark in the space is the LDBC social network benchmark. So this was a synthetic workload. It has synthetic workloads targeting mostly graph databases. And it has about 29 query types representing different social network actions, such as finding your friends or friends. And it also doesn't have any sharding information. So there's not sort of a representative benchmark out there, I'd say, for this very important application domain. And this lack is detrimental to both academia and industry. Academia, it becomes very hard to understand the limits of existing systems without this information. And it's also very challenging to evaluate new features and optimizations in the industry without access to be able to reliably reproduce these kinds of workloads. So we address this issue by introducing a new benchmark, TAOBench, that captures Meta's social graph workloads. So I'll briefly talk over some of the properties that we sought to capture with our new benchmark. So the first one is that we want to make sure we're actually accurately representing production requests. And here, we're trying to capture Meta's 3.6 billion monthly active users. They're sending tons of requests to the system, doing billions of QPS per second, and we want to make sure we capture this in a representative manner. We also want to make sure we express transactional requirements. So on TAO, they're both read-only and write-only transactions, and those are important both for correctness and for performance. We want to express sharding constraints as well, as I touched on earlier. This is not just system detail, but can have real impact on both what users see and also their growing regulatory constraints on where you can store data and how that can be stored. Also, we choose to model requests with probability distributions rather than using distinct query types because we're running tens of thousands of distinct query types per day. So it's not feasible to sort of replicate all of these in a benchmark. So we go the route of, for adaptability, modeling these requests with a small set of parameters that I'll talk about in a little bit. And then finally, we have a very large scale social network on which a lot of different applications are running. So we want to capture both the behavior of single as well as multiple tenants, especially how they interact with many different layers of applications and also shared product infrastructure that might have coordinated behavior. So we seek to capture these properties in TAOBench. And first, I'll talk about how we characterize the workload and some interesting things that we've seen. So specifically, we're looking at the TAO stack at Meta. It's operating at huge scale, so doing over 10 billion requests per second. And it's supporting a lot of diverse products. So things like Facebook, Instagram, WhatsApp, all run on top of TAO. And as such, it has a very simple API because it was designed to sort of do a few things well at scale. It now supports some flexible consistency semantics. Specifically, I'll talk about the transactions that TAO now has. So for single shard write transactions, MySQL is running under the hood, so it basically relies on MySQL for atomicity. And then cross shard, TAO has implemented okay, there we go. Two-phase locking, and I don't know why.
It's so complicated.
So complicated. Okay, two-phase commit. Yeah, the clicker doesn't even work. Okay, so for write transactions, we have two-phase locking, two-phase commit, and then on the read side, we've also prototyped atomically visible read transactions. I have a paper on ramp tab that was in VLDB last year describing some of this protocol if you're interested. Cool. All right. So in terms of the workload, we collected traces over 3 days. And mostly we found that the workload is very read heavy, so 99.7% reads. There are some writes and write transactions. We talk more in the paper about how we actually make sure this is like a representative trace. And we do see some patterns, like there's a daily peak in sort of workloads. But in terms of how this affects the access distribution, it doesn't do so that much. So we're confident this is sort of a representative data set. And we see a lot of different interesting features. I'll talk about 4 today. The first one will be about read and write hotspots. The second one will be about cache skew and how things are accessed in different layers of the system. The third one will be about sharding, collocation, how does load and sharding play into each other, and finally contention. So the first feature we're focused on today is read and write hotspots. So what this graph is showing, we have reads on the x-axis and writes on the y-axis. So each dot is a particular point, and these are like a sock. So basically, Meta, you can like something. When you like something, that actually creates edges between you and whatever object or post you just liked. So we're looking specifically at those keys. And we're showing the top 400,000 write keys because we find the tail doesn't differ significantly past this point. And what you'll see is that there's a cluster of points here on the left-hand side, and these are points that are read infrequently but written to frequently. So these can result for something like asynchronous jobs or migration tasks that are running in the background that cause a lot of batch writes. On the other hand, there's another cluster of keys that are read frequently and also written to frequently. And these result from, let's say Lady Gaga posts something, then a lot of people will be viewing that and also probably liking it. That leads to this cluster. So we see that there are read and write hotspots as we'd expect, but they can occur on different keys. And this behavior isn't always captured in existing benchmarks. The second feature we'll look at is cache skew. And what we found is that the caches are indeed effective, but there is still skew present in each layer of the system. So the system has 3 tiers. There's TAO in the middle, the MySQL database on the bottom, and the client-side cache running on top. So it's an additional cache layer with TTL. And you'll see that the vast majority of requests are served by TAO, some by the client-side cache, and 1% by the database. And this is for reads only, because all writes have to go to the database. So out of the most popular keys to that first layer, we find that 84% of them actually still overlap in TAO. So it means that a lot of those requests are first going to the client-side cache and then still having to go to TAO. And the reason for this is because a client-side cache can't actively request new information. So if you need anything more up to date, you have to go to the second layer. But that's really there just to serve. Sometimes there's like really, really hot keys. Like let's say someone posts something that's like very popular. That's just like an additional layer of cache for those like very extreme cases. And then looking at popular keys in TAO, we find that it's able to serve most of those requests. There's only 1% that's not being served by the cache, having to go to the database. And these are due to cache eviction or sometimes consistency misses. So TAO also guarantees, for example, read your write consistency. So if you read a key, it's not up to date, it doesn't have your writes, then you have to go to the database. The third feature we'll look at is hotkey collocation. So something interesting that we found is that a lot of hotkeys and write transactions tend to be on the same couple of shards. So to see this, this graph is showing the shards on the x-axis and then the number of hotkeys per shard on the y-axis. And we're showing it for the three main product groups that run on TAO. So for example, the keys we circle here, there's around 50 shards here, and they each have around 1,000 hotkeys. So you'll see by looking at this pattern that when it's not a simple distribution, and it is quite skewed towards a smaller number of shards. When we dug deeper, we actually found that most of these hotkeys aren't part of the same write transactions. So generally, some would say you want to probably spread out these hotkeys to different shards so that you have better load balancing. But something we found is that application developers were explicitly co-locating these keys to be on the same shards, because if you do need to do batched reads to the database, you actually get better performance. So we found that there's a trade-off between load balancing and batching of requests. Finally, the fourth feature is contention. So here we're looking at the distribution of contention of the workload. Specifically, this is showing a CCDF, so it's like an inverse CDF, so we can observe the tail better. So the frequency, so on the y-axis, on the x-axis, we're showing the number of conflicts per day for both write-write and write-read conflicts. We don't have read-write conflicts because there's currently no blocking reads on TAO. But what you'll notice is like the majority of cases, so these are high frequency, most of them have few conflicts per day, but there is quite a long tail, with some of them with very, very high number of conflicts. And we're showing per key type, which is basically a proxy for application use case of transactions. And digging deeper, we found that actually the vast majority of write-write contention is intentional. So basically applications are doing things they know are going to cause contention, but they still choose to do so because they're relying on the system to guarantee atomicity. So an example of this is there's like one application that was doing live video, and it basically wanted to annotate the live video, so it was like cutting it into time slices. And to do these inserts is basically sending redundant requests to the database to make sure by the time it needed those slices, they would be ready. But this would basically cause a lot of those insert requests to error out, and the application knew it could safely ignore those errors. So yeah, this is something interesting. We found that these conflicts are often intentional and can affect the majority of these requests that are using transactions. Cool. So after studying these features and others, we sought to capture this workload with a new benchmark and now describe our actual benchmark. So we open source Meta's production workloads, including 3 workload configurations that capture different aspects, including the overall TAO workload. We also open source a flexible framework with different adapters for databases already available, and it's very easily extensible to other systems. And how we capture the workload is with a small set of parameters that we experimentally validate. We show basically the workloads we generate are representative of production. So the parameters are here, and you can break them into 2 categories. The first are that they're directly generalizable to other data stores, so things like transaction size, what key is on what shard, the operation type, and request sizes. And then the second group capture properties that are expressed uniquely in TAO, but they also apply to other systems. So for example, a sock type captures things like bidirectionality. Do you allow an edge to also have an inverse edge to you? And those are important properties that are on social graphs. It's just how it's expressed in TAO is not necessarily the same as other systems. So the actual benchmark itself consists of scalable distributed drivers, and we have a simple API, very similar to like a key value store API. And as such, it's very easy to map to other databases. So we currently we have drivers for Cloud Spanner, TiDB, MySQL, PlanetScale, Postgres, TiDB, and UGoByteDB. So to actually validate that TAOBench's workloads are representative of production workloads, we basically matched on features that arise from the workload interacting with the system. Specifically, we looked at latency distribution and contention error profiles, and we found that, so this is an example workload, transactional workload, where we're showing the latency breakdown for both the production and the benchmark workload, and you'll see that we show that this is like statistically indistinguishable, and importantly, we're also replicating the latency tail, which has performance implications, and there's more details in the paper about how we go about this validation process. Cool. So now moving on to the benchmark, I'll talk about the internal and external impact that TAOBench has had so far. So for Meta, TAOBench has enabled a wide range of testing, including being able to experiment with new system features and optimizations, assessing reliability under extreme scenarios, as well as analyzing speculative workloads. So these might sound like pretty standard things you want to do on your system, but it wasn't possible at Tau scale before TAOBench was built. So I'll give some examples about how TAOBench has been used at Meta. So one of them is that we've been able to sort of prototype a lot of new transactional use cases. So previously, if a new application wanted to use transactions, it basically write that code, hope it worked, test it, and then basically not be able to see how it actually performed on production traffic until very late in the process, in the development process. And then at that point, they might notice, oh shoot, there's like a ton of contention errors, so we have to like rethink how we are doing transactions. And this led to sort of recurring delays due to these unanticipated errors. So the new process with TAOBench is we basically capture the workload they want to run and then measure these errors in a testing environment so we can quickly speed it up. So we did this for one application use case, and the production rollout actually showed the same breakdown of errors, indicating that TAOBench is able to allow for end-to-end testing early in the development process. For another use case, we measured the impact of longer lock hold times, which can result from network delays. Sometimes a region goes down, disaster recovery. So these are sort of extreme cases that are really hard to test in production. And we basically just artificially increased the lock hold time, and we found that after a certain threshold, you expect higher contention, which does happen, but after a certain threshold, the transactions just end up erroring out. And this demonstrates that in these cases, we want to fail as fast as possible to not occupy resources that could be used for other requests. And these are also, so this is showing that TAOBench is allowing us to test scenarios that are very challenging to assess in production. We also use TAOBench to test the effectiveness of a new API. So while Tau doesn't have full interactive read-write transactions, it does have things called preconditions. These are basically, you can read something, let's say you read X and the value is 1, and then you can condition your next operation, the write, say write to X only if its value is still 1. So basically integrity constraints. And the issue with these is that if you increase the latency of the time between when you're first doing that initial read and then it's write, the error rate grows. And this is because with longer time, it's likely that someone else has updated that value, so your precondition no longer holds. And with asynchronous crest, geo-distribution, also like shared data, so a lot of applications are touching the same data, this can be cause more and more errors. So with TAOBench, we're testing the effectiveness of a new API to see if by completing these operations only in the primary region, how much that reduces error rates. And finally, one last use case is looking at high fan-out transactions. So the transactional rollout has been ongoing for the past couple of years, and there are some application use cases that can touch a lot of keys, which can be very expensive. So we sort of went and evaluated the performance impact of this by looking at how latency and contention errors change. So on the graph on the left here, I'm showing the number of operations for both the existing cross-shard workloads and the high fan-out workloads, you'll notice that the high fan-out workload has a longer tail, and this results in a 24% increase in average latency, as well as increased contention errors, which are expected, but they do indicate that we probably need some additional optimizations if we want to support these kinds of transactions. And actually, both these workloads are open source, part of the workload set that we've currently released. Cool. So next, I will talk about TAOBench's performance on a number of systems. So we ran it against 5, which we listed up there. And excluding Spanner, the 4 on the right are systems we ran with 48 cores. So they're roughly equivalent, though we use cloud clusters, so the hardware is not exactly the same. And also keeping in mind that certain systems offer different guarantees. So TiDB, for example, only has serializability, while like TiDB does not, strongest guarantee is snapshot isolation. For Spanner, they do not publicly release the number of cores they have per machine, and each node under Spanner is actually like 3 nodes under the hood. So it's not, I wouldn't really group the Spanner results with everything else. But I'll point out a couple of interesting things. So one is we're running both workload A, which is like a write transaction heavy workload, and the overall read heavy workload. And we do see higher performance on workload O as expected because it's a lot more reads. We also find that there are performance differences on even the same system that our benchmark is able to show. So for example, here with PlanetScale, we see there's higher latency for write transactions than read transactions, and vice versa on workload A. And we also see that performance degradation varies across systems. So TiDB here its latency increases much more slowly than PlanetScale, in which you sort of start to see the latency impact even when you haven't reached peak throughput. There's more details in the paper about these results. It was sort of out of scope for us to explain exactly why each of these systems had the results they did, but it was demonstrative showing that our benchmark is able to highlight these differences, and it's a useful tool for evaluating different system trade-offs. Cool. So now I'll talk about some of the impact we've had in working with these companies and running TAOBench on their systems. So in CockroachDB, we actually helped them identify they had something misconfigured on Kubernetes, because when we ran on their cloud machines, our performance ended up being like 30% lower than when they ran them on their bare metal machines. So they're still figuring that bug out, but we also found that we're able to get fast path for simple queries, and also our workload is like very skewed, and that skew tends to happen around a couple of keys. But CockroachDB wasn't able to sort of spread those keys out onto different shards because they were detecting skew based on an average QPS versus QPS per key. So they are exploring a way for a smarter load balancing strategy. For PlanetScale, they weren't supporting insert into select queries, which we need for some of our requests. So they have now added that. TiDB has integrated TAOBench into their daily monitoring runs. It's very exciting, and that will allow them to verify the performance of new features. For Yugabyte, we helped them identify a couple of bugs. One of them was they had a bottleneck due to exclusive locks because they were using some Postgres monitoring extension, and they had sort of unexpectedly low performance on TAOBench, and we were able to help them identify that. And they also weren't pushing down filters for scans, so that was leading to a lot of out-of-memory errors when we ran on their system, and they've since implemented an optimization to reduce memory usage. So as a recap, we've introduced a new benchmark for social networks, and it's able to capture Meta's production workloads accurately, and also has a simple API that's easily extensible to other systems, and has already had impact at Meta and beyond. If you're interested in running TAOBench, definitely reach out. Be happy to help get that set up. And there's more information at our website. Thank you. Any questions?